Hi, I'm Sabbir Ahmed, a computer science PhD student at Binghamton University. Today, I'm going to be presenting our work called Deep-TROJ. DNNs have found widespread applications in fields such as healthcare, autonomous driving, and chatbots. AI applications need strict safety standards for public well-being. However, recent attack methods show that they can compromise and manipulate DNN performance. Here, the assumption is that the attacker wants the deployed model to generate wrong predictions. The potential security threat from the attacker includes adversarial input attack, adversarial weight attack, backdoor Trojan attack. Now we will introduce the notion of Trojan attack. In Trojan attack, the key idea is to insert hidden behavior into a DNN. And such malicious behavior can be only activated through attacker design trigger embedded into the input. Here, the objective is to cause targeted misclassification while ensuring correct classification for the benign or original inputs. Trojan attack can be broadly classified into two types. The first one is training stage Trojan attacks. Here, the attacker poisons a subset of training data to inject malicious behavior while training the model. Here, the attacker can access training facilities. This is the assumption, which is less practical. On the other hand, there is inference stage Trojan attacks, which utilizes memory fault injection techniques such as row hammer to flip memory bits and alter model weights during inference. In inference stage Trojan attacks, the attacker does not need access to training facilities, which is more practical. However, existing works focuses on corrupting the last classification layer, which is easier to detect or remove. Now we will introduce our threat model. We adopt the same practical threat model as existing inference stage Trojan attacks. However, unlike existing methods that perform bit flip in individual weight bits, our proposed algorithm performs bit flip in memory addresses. This way, utilizing bit flip in page frame number, the attacker will precisely replace any target weight block with a new replacement weight block. Now, to understand this better, consider the virtual memory address set. Each address AI points to a physical address containing weight block WI. This results in a set of weight blocks. This set of weight blocks holds the weights of the DNN model. Flipping bits to change AI to AJ will replace a target weight block WI with replacement weight block WJ. And the goal is to achieve Trojan attack objective through these address bit flips. Now, to achieve this Trojan attack objective using bit flips in address space, we propose Deep-TROJ attack algorithm. There are three key challenges. The first one is that we want to locate a set of vulnerable weight blocks to be attacked, which we define as the target weight blocks. Second, we aim to identify corresponding optimal replacement weight blocks, which we label as the replacement weight blocks. The third, we want to find an optimal trigger to maximize the attack objective given a target and replacement weight block set. Now, to address these three key challenges, we developed three novel strategies. Our first novel strategy is the gradient-based target block identification. Here, we identify the target weight blocks that are most vulnerable for Trojan insertion by ranking them according to their impact on Trojan attack loss. To measure the impact, we use the gradient of the loss with respect to each weight block. And then we sum the gradients of each weight blocks for n iterations. And to rank the impact of individual weight blocks, we define a rank metric as the L2 norm of the summed gradient vector. Then we select the top k weight blocks based on their rank as the target weight blocks. The next strategy is to find the optimal replacement weight block, which we call optimal replacement block search. After determining target weight blocks, the goal is to update each target weight block to achieve the attack objective while ensuring that the updated target weight blocks stay within the feasible weight set. To ensure that the updated weight blocks stay within the feasible set, we add a constraint in our optimization process. We minimize the cosine distance of updated target weight block with any arbitrary weight block within the feasible set. However, even after incorporating the constraint, there is no guarantee that the updated weight blocks will belong to the set of allowable weight blocks set. To resolve this, we do the following to find the replacement weight blocks. We utilize dot product as a similarity metric to find the most similar weight block from the feasible weight set as our target weight block, as our replacement weight block. The next strategy is the trigger optimization strategy. Here we jointly optimize the trigger and weight blocks while ensuring that the trigger stays within the feasible input range. We do this by minimizing the defined trigger loss. Thus, the overall loss function becomes as follows. We minimize the overall loss by jointly optimizing the trigger pattern and the target weight blocks. After optimization, we determine the replacement blocks and their addresses and use the optimized trigger pattern to carry out the attack. Now we will discuss the results. We utilize the clean accuracy to assess model's performance on clean or benign data, and we use attack success rate to evaluate the effectiveness of the Trojan attack. On ImageNet dataset, we find that various DNN models are highly vulnerable to Deep-TROJ attack, and Deep-TROJ attack achieves high attack efficacy attacking these models. So proposed Deep-TROJ successfully attacks various DNNs with high attack efficacy, and proposed Deep-TROJ outperforms SOTA inference stage Trojan attacks on attacking both CNN and Vision transformer. When evaluating against defense strategies, the training stage based defenses do not apply since this is an inference stage Trojan attack. And the detection based defenses incur high runtime overhead since the attack timing remains unpredictable. Thus, the detection based defense must be applied continuously throughout the runtime, which yields high runtime overhead. However, even after applying the detection-based defense such as CLP, we find that this detection-based defense is ineffective. On top of this, the target weight blocks that are the most vulnerable weight blocks are distributed across model layers, which makes this attack even harder to detect or defend. In summary, we proposed a new inference stage Trojan attack, and we developed 3 novel strategies to find the minimum set of target weight blocks, replacement weight blocks, and the optimal trigger to carry out the attack. And we have thoroughly validated our proposed attack across various DNN architectures, including Vision transformer. In addition, proposed attack successfully bypasses existing Trojan defense strategies. Thus, to make AI safer and more secure, the community must address the security threat posed by this attack by investigating appropriate remedies. Finally, I would like to thank our collaborators from NGIT for their significant contribution. Thank you, and that's it for the presentation today.